All right, now we're in lecture B. We're going to talk about the same material in lecture as we did in lecture A. It's called actuarial present value of a future benefit paid in a one-time payment of, in this case, $1,000 at some random time in the future for your customer. What I'm going to focus on in lecture B is pure Mathematica usage. I had a lot of fun in the 2 hours leading up to class trying to get this to work, and I actually ran into some trouble, and I made Mathematica crash. Would you believe it? Okay? I'll show you what I did that made Mathematica crash, and I'll show you what to do to avoid Mathematica crashing. It shouldn't crash for your problems. It crashed for my simulation. I tried to do a simulation, and it was just too much for it. Okay? Which seems sad to me. I didn't think it should be that way. So in this problem, now we're going to be doing the same thing. Washing machine, got a $1,000 warranty. We're going to pay that benefit at some random time in the future. And at this time, there's going to be drop-dead date of 20 years. Omega is 20. I'm going to do a triangular distribution for the lifetime of t. Meaning the graph looks like a triangle. For the PDF of t, it could be a symmetric triangle like this, centered at 10. Or it could be, that's an isosceles triangle, it could be a non-symmetric situation, something like this. Centered somewhere else, I shouldn't say centered, the peak somewhere else, like 15. That could be another triangular distribution. Or it could be where the peak is earlier. Maybe the peak is at 5 or something instead of 10 or 15. What's more realistic for real life? I'm guessing something like that's probably more realistic, where the peak of the PDF is in the higher values than compared to lower values. I'm guessing for real life washing machines, this is probably not a bad model. Probably not a bad model for the lifetime of the washing machine. Not that it would for certain have a drop dead date that's some particular number like 20, but maybe in all practicality, all these washing machines die before they're 20 years old. The formula for such things is piecewise, and it depends on C in kind of a complicated way. What I had Mathematica do here, we're just going to focus on big ideas. You don't have to know how to do Mathematica in the way that I'm doing here. I want you to focus on the big ideas. I used triangular distribution as a built-in thing in Mathematica that's going to model these different kinds of PDFs. And you see I have a PDF in front of it. The 0 to 20 means the domain is 0 to 20. The C there means the peak is going to be at some number C, which could be 10 or 15 or 5. I enter this, and Mathematica does produce a formula for me that's piecewise, which I basically reproduce there with my typing. 0 when true, that's a little confusing. Essentially, the PDF is 0 outside of the range between 0 and 20. I put the word otherwise there. Okay? So we mostly focus on the non-zero pieces, where the graph is non-zero. That's the PDF. Makes sense. You should take a minute or so to make sure it makes sense when t is less than c. In a generic picture here, the graph is a straight line with positive slope. I guess the slope is 1 over 10c. When t equals c, that's going to have a value of 1/10. The height of this triangle is going to be 1/10, no matter what c is, actually. Which makes sense, because now if you figure out the area of that triangle, 1/2 base times height, 1/2 times 20 is 10, times height, 1/10 is 1. The area is 1, no matter what c is. The height's going to be the same, no matter what c is. The other piece is a straight line with a negative slope. Evidently, the negative slope is -1 over that, -1 over 10 times 20 minus c. Does it come to the horizontal axis when t is 20? Sure, when you plug in t equals 20, there you get 0. Does it match up when t is c with the other piece? Plug in t equals c here. The 20 minus c's that you get canceled, then you get 1/10. It does match up. The graph is really the formula for the graph. It looks like that. Here's some stuff I did to do simulations for the lifetime. We're not talking about the present value of the payment yet. This is the lifetime of the washing machines. Again, you don't need to know this code. Let's just appreciate what it shows us. And this one didn't crash on my computer, so why is it crashing now? Let's see, what are the others saying? Rectangular array, expected position 1 and mean 1. Oh, it's because I changed the names of things here. I'm putting t's in there to emphasize it's a variable t. And I forgot to do that. Okay. Now it's working. So what is this showing? This is the lifetime of the washing machine. It's a simulation. Simulated lifetimes are the black dots. I'll let n go all the way out here. There are 100 black dots there. Each black dot represents one washing machine. How long did it last? It's a density, a PDF, probability density function. The points are most dense where the graph is highest. They're less dense over here and over there. That's why it's called a density. It is kind of like a mass density, actually. I happen to shade the area between 5 and 15. That area represents the probability that a randomly chosen washing machine will last between 5 and 15 years. That probability is 0.75. For this simulation of 100 washing machines, 73 out of 100, close to 75%, actually lasted between 5 and 15 years. I can change A and B. By the way, I will put this on Moodle, and you can download this and play with this if you like. If I change A and B, I change the interval that I'm thinking about. Now it's essentially age 2 to age 18 or so. Probability of the lasting between 2 and 18 years is about 0.95, and in fact 95% of the simulated data was between those two numbers. I can change C though too. Where's the peak? I can change C, look at that. I can change the nature of the distribution. This one is probably more realistic. And if I went back to, well, let's re-enter it to get back to A equals 5 and B equals 15. If I make it more realistic, what happens to the probability? The probability of being between 5 and 15 years looks like it's going down there. You see that that number there was going down compared to what it was when it was here. So that's one thing this more realistic situation would imply, is the probability that lasting between 5 and 15 years is less if the peak is up closer to 15 or 16 than if it was at 10. One other thing I forgot to mention is the red and blue dots. The red dot is the mean of the data, of the simulated data, and the blue dot is the median of the simulated data, not the distribution itself. The mean and the median of the distribution itself are supposed to be the true theoretical values, and these are supposed to be close to those theoretical values, is the idea. We're comparing means and means of data versus means and medians of distributions. But now we want to go on to Z. I need to use the CDF, just like I did in lecture A. When I was doing this kind of stuff, I need the capital F if I'm going to come up with the capital G. Capital F being the CDF for T, capital G being the CDF for Z, the present value of the future payment. So there's the formula for capital F. Now we do the transformation. We use this equation to convert to Z. This calculation here is the exact same thing up to the same point. By the way, the fact that it is the same thing is because of the fact that the 1,000 e to the negative 0.05 t is the same every time. That's why it's always the same calculation there. If I change the 1,000, if I change the interest rate, then the calculation would be a little different. But we're keeping the $1,000 and the interest rate the same for all of our examples. So that's why this calculation is always the same so far. As far as solving the inequality for t, I did it as an equation. Solve can be used to do that. Negative 20 log of 0.001 z is the same as negative 20 times natural log of z over 1,000. I created g in this way. Compare what I have here with this. I entered it. This was the formula that I got. Kind of complicated. This is sort of the level of complication for yours, involving the logarithms. Here's the CDF of g. Yours is not piecewise, though, so that's nice. Mine is piecewise. It's piecewise because the triangular distribution is piecewise. You just have straight lines that are not piecewise. So yours is not quite as complicated as this, but it does involve logarithms in similar kinds of ways. Can I plot the CDF for a particular value of c? Yep. There's the CDF, and notice it goes up to 1 when we get to $1,000. This is the value of z, not t. That value right there is 1,000 over e, about 368. Right there is where this function is 0. Okay, now I got into the places where I was starting to make Mathematica crash. I'm getting close to that place at least. Down here, I actually was trying to do the simulation for this situation. And it was this particular code with a manipulate where I was trying to simulate the data and also allow myself to change the A, the B, and the C. It just couldn't handle it. It was too much for Mathematica. It aborted my calculation without me saying abort. It just said, too hard, too much work, I give up. Mathematica gave up. So what did I do? I said, okay, let's try to see what we can find out without manipulate. Okay? It's ultimately the manipulate, the fact that it tries to do this for lots of different values of A, B, and C that made it crash. So for example, up here, let me, punchline there. Let me graph these different distributions. Let me even add one more to it. Maybe the most realistic one, where the peak is at 15, for example. G sub 15 of z. And let's make that one be magenta. So I'm going to graph 4 different PDFs here for different C's for the original triangular distribution. Where is the original triangular distribution highest? One where it's real close to 0.1. So the highest point's real close to the vertical axis. One where it's symmetric at 10. One where it's more realistic at 15, like that one. And one where it's near the end at 19.9, which is close to almost just a straight line going up. It goes down at the very end. Plot all 4 of these. Oh, why is it not plotting? Did I not enter it? I probably didn't enter it. Okay, let's make sure we got G entered. Enter this. Now it should work. There we go. Ignore the vertical line here, by the way. I don't think that's part of the graph. I think that's Mathematica just connecting dots blindly. The green graph should just go down. These are the different the different PDFs for Z. The red one is when T has a PDF whose peak is close to 0. What is it telling you? It's highest in the higher values of Z. Ignore that line too, I think. In other words, most of your present values for customers, future payments, are pretty high. Their washing machine doesn't last very long. Which is what this would tell you if the peak is close to 0. Most of the washing machines are going to die earlier than later. At the other extreme, the green one, C is 19.9. Most of the washing machines are going to last a long time, though they all die by 20. The green one, the higher values are in the lower Z values. Most of the present values of the future $1,000 payment are pretty small because most of the washing machines last pretty long. And the other ones are in between. Well, maybe these lines are supposed to be there. I mean, this is kind of almost vertical. Maybe they are supposed to be there, I guess. The most realistic one is supposed to be the magenta one. I'm pretending at least. Most of the present values are going to be sort of between 400 and 600, you might say. What's the mean in each case? Actually, I can plot the mean as a function of C. This takes a few seconds, but it does make a plot. Oh, wait. I did enter them. Takes a few seconds. It did make a plot in my computer. This is perhaps the most useful graph that I'm going to show you here, once it shows up. Come on, come on. It's running still. Okay. Is my computer better than this? Mathematica's speed is somewhat hardware dependent. Come on. It says it's running. I'm plotting the mean of Z for different C's. As C goes up, there we go, the mean goes down. The present value, on average, is smaller when C is higher, because most of the washing machines last longer when C is higher. And this is really useful, because, again, these kind of distributions, I'm guessing something like this is not too far from reality. I'm not a washing machine expert. I don't have the data, but I'm guessing something like that's not too far from reality. And so what this graph gives me is for any C value that gives you the peak of the distribution, which is not the same as the mean or median. It's, you might call it the mode. It's where the highest value of the graph is. If I happen to know that based on past data of a washing machine model, near what year, 13 years, 14 years, 15 years, 16 years, do most washing machines fail to the nearest year, if you round to the nearest year? If I know that information, I can use this graph to estimate the present value. And so if they mostly last 15 years, close, as the most common length of time they last to the nearest year, I could go up to the 15 year, go up to the graph, and go over and see that around 575 is the present value of that $1,000 payment. So I need to charge my customers at least $575 for the warranty. But again, you want to profit, so you want to charge them more. But that's really expensive for a washing machine warranty. In reality, it's partially because the $1,000 benefit is high. That's one reason why the average is so high. And for another reason is I think warranties are typically for only 1 year or 5 years, not for the lifetime. I mean, sometimes you get lifetime warranties, but to make sure as an insurance company that you can cover the warranty, if you're pretty confident that the mode is 15 years, you better charge them at least $575 for the warranty. More than that to make a profit and cover your costs. Not just cover your costs of making that future payment, but also, you know, your employee salaries and that kind of cost. So this is real practical, okay? This is practical stuff. It's complicated stuff, but it's practical. Before we end lecture B here, I do want to remark that, well, first of all, I forgot to let you know, make sure you tell me in an email here after class, I prefer soon after class, whether you plan to take differential equations in the spring. And the 3 options are, well, 4 options: very sure, somewhat sure, not so sure, and definitely not, I think, something like that. Send me one of those 4. Because we're trying to figure out times for classes and whether we offer our second section online. Also, next summer I am trying to offer a financial math class on actuarial stuff to help pass a financial math test for actuaries. It's got to be approved by the administration yet, so this is not set in stone. but I'm hoping to do that next summer if you are interested in the possibility of being an actuary. And the kind of math you need to know for that is just calculus 2, actually. You don't need to know differential equations or multivariable calculus for that. Okay? There is some business kinds of stuff in there about investments, stocks, and bonds, and that kind of thing. But we learn that in the midst of the course as well. All right, we'll end lecture B there.